And then Chrissy, hi, do you have questions?
I mostly just came to hear other people's questions.
Okay. Same situation with Sam here. But if
Thank
you,
you.
yeah, I'll hang around and wait to see who comes in. But if you can think of any questions, logistics, anything, just let me know. Otherwise, I will work in the background until more people come in with questions.
If you wanted to talk again about hydrophobic interaction chromatography, that would be cool.
Okay, yeah, I would love to talk about hydrophobic interaction chromatography. We use it a lot. Um, so, hydrophobic interaction chromatography is basically your medium is a hydrophobic resin. So, interaction is via a weak hydrophobic interaction. It's not strong hydrophobic interaction because if it's strong, it's so hard to get them off the column. So your components usually are proteins. It's very common in protein separations for semi preparative type of work. So what happens is when you prepare your protein mix that you want to separate, you might want to be separating only protein from carbohydrates. Say you don't want to separate proteins from each other, but just protein from another set of constituents. What we do is we usually solubilize the sample in salt, solid, high salt solution. So at that point, your protein charges get blocked by the salt, charges from the salt. So when you inject the sample on the column, then the surface of the protein that is hydrophobic can now interact with the hydrophobic surface of the column because there's no charges yet because all of the salt has been blocking those charges. Then you want to separate. Let's say if you have a carbohydrate is not going to react with the column. They will leave the column early and then the protein is interacting. If you want to separate different components within the proteins, then you decrease the salt concentration slowly over time. This way, the proteins that are more charged than other will start coming out sooner, and the proteins that are more hydrophobic and with less charge will stick around in the column until you put completely water, no salt, and then they start coming up. So basically, you're separating based on differences in surface hydrophobicity of the protein and how much it's charged on the surface.
Okay, that makes sense. Thank you.
Good.
So in that case, when you decrease the salinity, what would you expect to elute out first?
Yeah, you expect to elute the more polar protein, the protein that is less hydrophobic on the surface. So the more the protein is hydrophobic, the more it's going to stay on the column until you remove all the salt from the running buffer and it becomes water. Then they all come out at that point. But we have experienced very hydrophobic proteins, especially proteins that coming from a commercial source. They are being processed in a way that the protein is denatured, so they get stuck on the column. Even with water, they don't come out. So we force them to come out with zero point 0.1 normal NaOH solution. So basically, we're adding charge to the protein by running it under basic conditions. But you don't have to worry about it. That's more of a research work that if the protein really gets stuck and doesn't go out, there are ways to get it out by making it a little bit more charged by changing the pH. Yeah.
Okay, thanks.
Hi, Chris.
Good morning.
Good morning. Sam and Chrissy here are mostly sitting around waiting for people to ask questions. So if you have questions, shoot away, and then
Yep.
they can follow up on any of those questions.
Well, Sam and Chrissy have the same idea I do, is that I have some questions, but really I am happy to be a wallflower and just kind of hear what questions other people have to say. But I do have something I'd like to start out with.
Okay.
When we take a look at atomic absorption, I know that the method or what was used in lab was flame AAS, which uses absorption. But then I want to compare this and consider ICP AES for simultaneous simultaneous readings of minerals, but I understand that that is emission, not absorption.
Yes.
And now, when I bounce back to AAS, I know that I have a monochromator that is going to be separating my wavelength into that one lambda and then going into my photomultiplier tube. Now, but for ICP AES, I'm not sure how to describe that detector properly. Would you be able to give a description of that detector?
Yeah, so if you remember in class, I told you don't worry about the physics of this detector, just know what it will give us. So basically in ICP AES, you have the plasma. It's the source of ionization, I mean, not ionization, atomization, and source of excitation at the same time, which is different from AAS, where you have a lamp for excitation, you have the flame for atomization. So the plasma does both, and and then what happens is when the atoms in plasma are excited, they are going to go back at some point to the ground state. And as they go back, they are emitting radiation that are specific for that element. And that's why we can detect these elements, because the wavelengths that they emit are specific for these elements. But there will be other elements, and all the elements are emitting radiation at the same time. So what happens, all this radiation goes to this detector where you really don't have a monochromator there. So that's the Ishel detector. So that detector basically converts the individual wavelengths to electrical signals that we can detect simultaneously for all of the elements. So it has a prism in there, I believe, and then it has its specific physics where it converts these emitted radiation into electrical signal. So that's really all you need to know, is that detector allows simultaneous detection of all of the wavelengths hitting that detector simultaneously. And we
Okay.
will be able to identify or to quantitate like you do with the PDA. It's different than the PDA, the photodiode array detector. It's a different story, but it's giving you also different wavelengths. And as an analyst with the software, you can select your lambda max for each element and determine the absorption, the emission, sorry, at that, and use that to quantitate. So you would have standard curves with standards that you have run and your samples, and you do the same thing. So you plot standard curves, and you select the one emission wavelength that you want to quantitate at.
So for PMT, it's more an understanding of the functionality and not necessarily saying something like with an FID where I have to describe really how it functions.
Oh, but be careful. PMT is not the detector in ICP. So
Oh yeah, it's a different.
yeah, PMT, I explained it in class, photomultiplier tube detector, where you have your electron that hits a cathode, and in the detector, and the cathode emits an electron and goes into multiple diodes.
Yep.
It multiplies the electron, so you have intensified signal. So that's a photomultiplier tube, and you use it to detect. You will have a photomultiplier tube that you selected at a specific wavelength to determine the absorption. Okay, and there are also like you have equipment where you have multiple photo multiplier tubes at the same time, so you can do analysis for multiple elements at the same time, or you can have it consequential, one photo multiplier tube, and you can change the wavelength each time, and you measure multiple elements, and then you have the issue detector, and we're talking ICP here.
Hmm. Okay, thank you.
Yeah, you're welcome. Anything else? You can keep me busy, or I can just work in the background, but I'm here to answer questions. So if you have more, Chris, shoot.
I don't know if we actually need to know this much in depth for the exam, but just out of curiosity, you mentioned the guard column is to protect from impurities and also from like things that may bind the column instead of the analyte of interest. But how do you ensure that your analyte doesn't bind to the guard column?
Oh, yes. So basically, your analyte doesn't bind strongly to the column. So it continues to move along even though it's interacting with the column. So it's all about it's moving along. You remember the concept of theoretical plates.
Mhm.
So you have equilibriums, multiple equilibriums that happens. There is no static. It's moving because you have a mobile phase. So your analyte is moving. It's interacting with the column, but it is in a not a static way. It reaches equilibrium and then moves on to the next and moves on to the next. However, an impurity that binds strongly to your column doesn't move along. It would just bind, sits there, and blocks potential functional groups that your actual analytes need to interact with and move along the column. So that's what the guard column is. It's kind of like a filter. It filters those impurities that would just stick and not move along with your mobile phase.
Okay.
Does that make sense?
Thank you.
Yeah. So Chris, just to make sure that the point came across well, is with the atomic absorption spectrophotometry that we did in the lab, you had one detector with one photomultiplier tube. When you go to ICP, the unit is more advanced than AAS, so it could have different detectors. You could have a photomultiplier tube detector, but you can have multiple in that unit. So you
Okay.
can have multiple photodiode array photomultiplier tube detectors, sorry. And then you would be detecting 4, 5, up to 8 elements at the same time.
Oh, sure. Where your light would hit a grating that would separate those
Yes,
lambda, and then they would go to the array of PMTs.
yes, exactly.
Okay.
And that is simultaneous detection, but limited to the number of PMTs that you might have.
Mm-hmm.
Facial detector is basically the most advanced of them all, where you can do almost all of your elements simultaneously, because then you have all of the light that is emitted that goes into your detector, and you have prism, and you get all of the wavelength hitting the detector and converting each one individually to electrical signal.
Mm-hmm. Okay. Yes, that explains it very well. Thank you.
Yeah, good.
So when would someone want to use atomic absorption then if ICP can do all this?
Oh, they would use it if they don't have ICP in their facility. ICP,
Okay.
especially the one with that issue detector, is very expensive. So if you work in a big company or a big analysis lab and they have the funding to obtain an ICP, that would, and you have a routine mineral analysis, then you would definitely not want to use AAS. That we have actually ICP on campus in the soil department, because they do always analyze the mineral content of soil. So they do have a very good and advanced ICP unit.
Okay, thank you.
Yeah, you can take this time to study, and as you study, if you come up with questions, let me know. If you want to know structure of the exam, any general questions, let me know. Otherwise, I'm here. I'm listening. Anytime you can ask a question, I'm listening. My eyes might not be down here, might be up here, because I'll be multitasking until you have a question. But you can interrupt me anytime. This is the time for you.
One of the things, Pam, is that when I take a look at labeling, so our first lab, I'm not taking away a ton of information for labeling. Since this was one of our laboratories, I'm assuming there's going to be a question about labeling. But the big things that I am storing away about labeling is the making claims and making sure that if you have a claim for calcium or a claim for protein, that the minimum amount that is on your label is what the label states, that you can't have under that without misbranding.
Oh, well, you have to know the numbers. So there is if you are adding a mineral or adding a protein and you're claiming, you have to be at 100% or more. If it is a nutrient that is already present, you're not adding it. If the protein percentage or total carbohydrate percentage, or you're not making a claim, it's already there. It has to be at least 80% of what you say there is. So that's what you really want to know, is the compliance for those different components. If you have anything added and you're making a claim, you have to be at 100%, not less, of your claim. If it's just there, at least 80%. For fats and sugars specifically, you should not exceed 120% of what you claim, or the calories. So these are the things that you want to remember about claims and compliance, I would say. You want to know what are the current components that you would see on the nutrition label. So the one that is most recent. So sometimes I tell you list 6 components or list 4 components, whatever that you would see on the nutrition label. So you want to know what they are. When I say nutritional components or constituents, I don't mean calories. Calories is not a constituent, it's a calculated number you get from constituents. Yes, it's on the label, but it's not a constituent per se. So constituent is your protein, total fat, saturated fat, total carbohydrate, fiber, soluble sugar, added sugar, calcium, iron, potassium, sodium. These are the constituents that you would see on the nutrition label.
Are there any dates relating to nutrition labeling that we should know, or certain? I know there's like the FD&C that was for like or there's like a.
Oh,
I know,
the
like,
dates? No, when I
yeah,
give
okay.
you the dates, it's just for like telling you the story of the nutrition label, because it's good to know how it transitioned over the years from no nutrition labeling, just the name and the common name, to list of ingredients, to specific constituents, and then it became more elaborate over the years. But no, I don't expect you to know the different acts and the year. It would be good to know for college ball, Sam.
Okay, yeah.
That's the trivia there. Yeah, for the nutrition label part, I would say the lab was mostly you're running a program, right? So there won't be any questions related to the program. It was the intent of the lab was to, have you know and be familiar with one program for nutrition lab if you go and work in industry, but there will be a little, every company might have a different type of a program. Tech Wizard is one of them. And then it's helpful for a capstone or product development class to know this in case you want to use it to create nutrition label. But I won't be asking in the exam anything specific about the program itself or how it runs. So the questions would be mostly related to what we covered in class for that particular topic.
Okay.
One thing I would say too is when you study, if today is Thursday, maybe by end of today, after you feel that you had a good chunk of studying, I recommend to solve example from last year without looking at the questions. Don't solve it and looking at the question at the same time. That doesn't help you. You feel like, oh yeah, I know this. No, try to solve it yourself. And after you solve it, you compare to the key. And if you had it down, then great. If not, then look to see why. That's kind of an exercise to get you prepared. Of course, the questions are going to be different for sure, but at least you'll know with how you studied, how much you're prepared. That's kind of your way of knowing how prepared you are.
Could we go over the difference between IR spectroscopy and then UV vis spectroscopy, like when you would use one over the other?
So IR spectra and
UV.
okay, so UV has limited detection power, like identification power. I showed you this example of its limited identification power when we were doing the HPLC lab and looking at caffeine. Even a PDA, a photodiode array detector, is not enough to give you really nice fingerprints. So it has limitation because if you have two compounds that share the same chromophore, but they're different in different structures, you won't know. You just see the same absorbance spectra. However, with IR, a lot of the work that is done with IR is identification of different components because it looks at the bending and stretching of specific bonds. So within one molecule, you can see different peaks within one molecule, and each peak represent a percent transmission, which that's a difference than looking at percent at absorption. You look at transmittance over wave numbers. So if you listen to that lecture, you would know what I'm talking about. So, and then you get this nice spectra of that identifies very specific functional groups. So this is a very powerful identification tool compared to just simple UV absorption or fluorescence. So that is why it is powerful. And also there is the mid-IR and near-IR that you can use this powerful information to determine percent fat, percent protein. You can calibrate it with the wet chemistry methods. For example, you can calibrate when you're doing you use a lot mid-IR in industry to monitor milk composition quickly on the line during processing and production, but you equilibrate your mid-IR instrument using Modiner method for fat that we just covered using Keldal or Dumas method for proteins, which we will learn next week. So you have to use official methods of analysis to calibrate. So you just prepare standard samples that vary in concentrations. For example, many years ago when I started teaching, I used to take students to an analytical lab that they process dairy products and then they would see the different testing that they would do. And one of them is the mid-IR, and they would see how they prepare milk samples that are standards that have different fat content, different protein content, different lactose content, and they use these milk samples as standards to calibrate the instrument. So they use these different milk samples to run all of the, like the ashing, the moisture, the fat, the protein, using the wet chemistry methods. And then they go back and calibrate the mid-IR. And then once they have calibration for each of these components, then they can run multiple samples as they come out of the processing lines. So yeah, so it is mid-IR and near-IR instruments are really used as online testing, quality testing, quick testing, but they are calibrated by official methods of analysis. That's a very important thing to know, that they're calibrated. It's good to know some uses, and I give a lot of examples of uses in that recorded lecture. So you just make sure to know these uses. They might ask you what are common uses, just exact same question you just asked me. That's a common question.
Thank you.
And understanding on what basis the detection is. It's based on the vibrational energy and the vibration of the bonds. That's why we talk about bond stretching and bending, because this is due to the vibration of the bond. And that's what is detected in the IR region.
So IR and UV vis would only be the bonds between atoms, but nothing on like the electron level, right?
IR, but not UV vis. UV
Oh, right,
vis
okay.
absorption and UV vis absorption and emission can be on electronic, and there will be some also vibrational energy. But for IR radiation, it is specific for bonds. So you can do atomic analysis of elements that are atoms using IR. Yeah,
Okay.
in atoms, there are no vibration, no rotation. So you can't use IR for atoms. That's a good question.
Touching back on UV vis, there are a considerable number of slides on UV vis, which makes me wonder, in what applications would you use UV vis instead of a different detector?
Oh, UV vis is used in so many applications. And if you, okay, I need to open the lecture to point you at the slide where I talk about applications. Let's see. UV vis. So go to UV vis lecture if you have it, if you have the slides in front of you. And then go to slide 4. And here is a slew of examples for UV vis. So you can do qualitative, you can do quantitative. quantitation of macro components, quantitation of micro components. Another example is enzyme-linked immunoassay. A lot of the HPLC chromatography is linked to UV detection, visible detection. A lot of the assays that we use in the lab, total carbohydrate, biphenolic sulfuric assay method. We will learn it when we cover total carbohydrate lab,
So,
vitamin, minerals.
Cam,
So,
UV vis could have been used as a replacement for the variable wavelength when we did caffeine.
okay, so UV vis spectroscopy is kind of a category of spectroscopy, and then you have detectors. So the UV vis spectroscopy is telling you where you can apply it, what it is. But in every chapter we cover, depending on what's the component we're analyzing, there will be different types of detectors. Some detectors utilize UV visible spectroscopy. Some detectors don't utilize UV vis spectroscopy. So in caffeine, we used variable wavelength detector. That's the name of the detector, and it's utilizing UV vis spectroscopy. But it
I
has,
see.
yeah. If you want, we can go through questions from the exam together. If you feel like this would be helpful, we can do that. Or just continue asking me questions. What would you like to do?
I think we should probably go over a couple of them on the exam
Okay.
one Cam.
So open the one without the answer. I mean, I wanted you to solve it on your own, but I can at least like see how you think about these questions and if you understood what I'm asking for. So that still to allow you the opportunity to study and then solve it on your own. Let me open it myself and you can go to Canvas and open the one that doesn't have the key.
Was there a table that compared all of the detectors? Do you know off the top of your head?
Table that compared all the detectors, no. But in the HPLC lecture, for example, there is a slide that lists all the detectors. And I would differentiate between them. So either you've taken notes or you can go back to that lecture on HPLC. So there is a slide for that. Now, Gary has a little bit different style. So he spent some time talking about the physics of the detectors. I can tell you I will not ask about the physics of the detectors,
Right.
but I would want you to know how the FID works because you have had lab on it. So you want to know how the FID works, not so much the physics, but how do you get a detection? So flame ionization detector. So there's a flame. So your components are carried by the gas, they get to the flame, they get ionized, and then there is a potential running, so you will detect a change in current when you get the ions, and that is linked to the concentration of the ions. So yeah, you want to know this much, but not so much about the physics of the detector itself. So another universal detector in GC, for example, is thermal conductivity detector. So it's also good to know. It's going to come again in when we cover protein analysis using a nitrogen analyzer. So the nitrogen analyzer that we use in the lab or in general that is based on the DUMAS method, the detector is thermal conductivity detector because we're detecting nitrogen in the gaseous state. So we use thermal conductivity detector. So it's good, very good to know the difference of thermal conductivity detector and flame ionization detector in GC and how they different. What are the advantages and the disadvantages of those and where they are used. So I think if you spend time understanding these two detectors, that would be good. Yeah, of course, you want to know that there are other detectors, maybe a couple of other names, but I usually in my exam focus on what is most common, what you learn in the lab, and such. Yeah. So where was I going? I was going to do what?
The
You
exam.
were, yeah, you were
I was,
asking us to pull up the exam and look for questions we might have.
oh, okay. The exam. I was like, I opened my window and I was like, what am I going to look at? Yes, Chris, you had a question?
No, I was answering where you were going. Sorry.
Oh, no, that's good. But Chris, I think asked a question.
Oh, no, I don't have a question. I do need to excuse myself for a second to get my kids going for school this morning. And
Okay.
I'm just going to close off my video.
That's fine. I'll be here till 10. Okay. So we can.
I do
open-
have a question on it when you're able to pull it up.
Yes, let me see where it is. So do you remember what was the year next to the exam?
I'll just go back and
2019.
2019?
Mm.
Okay, because I have exams from 2013 till now. Well, actually, it goes back to the first year I taught, 2008.
I've heard that you have superb organizational skills in your Google Drive, so I believe that.
Yes, yeah, I do. I love organization. Keeps me sane. All right, so yes, exam fall 2019. Here we go. I have it open in front of me right now. Okay. So Sam, you had a question?
yes. So I guess for question 4, where it's talking about investigating a case of possible mislabeling of decaffeinated coffee. It says
Yes.
you observe 3 peaks alluding close to each other. How would you determine for sure which peak is a caffeine peak?
So question 4 and
Oh, part C.
part C. Okay. Yes. Yes. So how would you determine?
Oh, right. So I would think, I mean, I guess I'm not entirely sure because ideally you would just have a peak at the appropriate retention time. And then I would think you would just pick the closest peak to your expected retention time.
Well, that's the first, yeah, that's your first approach. However, if you have a case similar to the decaf coffee case that I pulled during lab, or at least during that video that you watched in the hall. So the decaf coffee had like 3-4 peaks around that retention time of 16 minutes or whatever for that. So if you have now you want when you answer this question, you want to think, okay, do I have a variable UV detector? Do I have a photodiode array detector? And what can I do with either? Let's say you have the simplest one. You have the one that doesn't give you a scan, it just gives you an absorption at a particular selected wavelength. So that your lambda 272, whatever it was for the KFE. So it will give you just an absorption. So you have all those 3-4 peaks and you're only seeing this absorption and which one it is. That one is
Bill,
at
do you need anything?
5 minutes and the other one is at 16 minutes and the other one is
I want you to put that away now.
there is no way for you just to look at this chromatogram and say, this is for sure is my caffeine. No way. even if you have similar retention time to your standard, you have 3 or 4 similar retention time to your standard. So in this case, your only hope of identifying is to spike the sample.
Oh,
So
okay, that makes sense.
you would take the same sample and spike it with a standard caffeine. This way, the peak that increases would be that one that you want to quantitate before spiking, without spiking. So that's your way of doing that. Now, if you have a different detector, a stronger detector, a PDA, and you can then look at the spectra, the fingerprint, and try to figure out which of these peaks have the closest spectra to your standard.
Okay.
Another one, if you want to be clever, which I had students answer that before, and I went back and adjusted my key because I thought, oh, that's a good answer. I wasn't aiming for it, but yes, that's a good answer. Linking it to an MS. Simple. If you have MS in the lab and you have all of these peaks coming out and you're just confused, you can just, instead of observing UV spectra, you can observe molecular weight by MS. So yeah, that's a smart answer. I wasn't looking for it, but one of the students answered it, so I adjusted my key. So yeah.
Okay, thank you.
Yeah, you can
So
convince
if
me there is not, you have a key, right? But there is always creativity in answer, and if it makes sense and it's logical, sure, you'll get the points. And if you think, okay, so this year in particular, I'm not grading at all. So I just don't have time to grade anymore. I used to grade everything, including lab reports and quizzes and everything in the past. Now I'm just too overwhelmed, so I have my TAs grade. So my TAs go by the book, you know, they're TAs, they're just graduate students. They don't have the experience of many years of teaching. So they go by my key. If you feel that you were deducted points for an answer that you think is different from the key, but you think it's still logical, please don't be shy. You can come talk to me. Okay. Then I will look at your answer and I might give you points back. You don't have to go back to the TAs. The TAs are going to argue that, oh, I'm following the key, which that's what they're supposed to do. But I put the key and I have years of experience, so I can see if your answer different than the key, but yet can be considered correct. So keep that in mind and tell your friends too. I didn't mention it in class, but keep that in mind that I come to me if you feel that you are deducted points that need not be deducted. Oh yeah, so we said we're gonna go through the exam questions and see how you understand each of these questions. And you can tell me if you understood it, if I can tell you if you understood it correctly. We can do that. We're not gonna solve it because I want to give you the opportunity to solve it yourself. But so if we look at the first one, you are planning a nutrition label for a protein enriched beverage. So here's your key, right? Protein enriched beverage. Intended for athletes, and you intend to make a protein claim. So the answer is in the question right there for you. Should the label include percent daily value for the protein? Yes.
Yeah.
Okay. Explain your answer. It's very simple. right? Yeah, they are claiming they're adding protein and they're claiming a protein claim and they are directing it to athletes. Yes, they need to. So your answer is in the question. So you would just answer it based on what was given to you in the question. Suppose the measured protein content turned out to be 12 grams per serving instead of 10 grams per serving. Would this be a problem?
I think you had mentioned that we'd be more concerned with fats or sugars being over than nutrients, right?
Exactly. So for protein, it's fine. They want to make sure they're at 100% or greater from what they're claiming. So if we did the experiment and we found 12 grams of protein, then that's okay.
Mhm.
All right. So you are considering adopting a new analytical assay in your laboratory to analyze protein content in the protein-enriched beverage. So how would you validate the method in terms of accuracy?
Would this be the relative error?
Yes, but how would you, what is the equation of the relative error?
Oh, it's the the measured value minus the expected value over the expected value times 100.
Okay, so how do you, what's the expected value? How do you know what the expected value is?
You need to start with a reference standard.
Yes. Okay, so you want to spell this out for me. When you say, okay, we need to start with a reference standard that has already been, measured for protein content. So then we can take that reference standard and utilize our new method and see if we can get to the same result, outcome. So you can say that. That is absolutely true. But you can also say something else. What can you say as well? If you don't have a reference standard, you only have your sample.
You could use a known assay, a known verified method to get
Exactly.
that quantity or to get to that information.
Yes, exactly. So either answer is correct. I just want you to convince me in a way that this is how you're going to validate. Either you have a reference standard with a known protein content and you measure it using your new method, and if the result is matching, then you can measure your own sample and not worry about it. Or you will take your sample, one sample, you don't have a reference, and you would just measure it using a known official method of analysis and your new method. And then you can compare your true value you would take from the known method or the official method. Then you can determine the accuracy. So use these keywords. Okay, I need percent relative error, but where is my, what value I would use for my true value? Then if you want to use the reference standard way, you can do it. If you want to compare official method and your method, you can do it that way. So yeah, so that's, your answer needs to be complete. You want to make sure that, don't think that we know what you know. We don't know what you know. Don't just say percent relative error and leave it at that. Okay, so yeah, where are you going to get your true value here in this situation?
So you'd want us to spell out the equation if we use one?
No, not necessarily spell out the equation. Just say, if you say you want to use percent relative error, you can tell me where will your true value come from. I'm going to assume you know the equation. I don't want to see the equation. I just want to know that you understand the logic and you spell out your logic.
Okay.
Since we are
Yeah,
talking about
take time explaining your answer. Don't assume that a simple answer, a short, simple answer is going to give you the point. This one, for example, has 10 points. So I have 5 points for each of the sub questions. So the A and the B. So think, how are these 5 points going to be distributed? It's not going to be distributed for a simple yes, no answer or use percent relative error. You're not going to get 5 points for just saying use percent relative error. No, look at the points and think, oh, they're looking for something here. So yeah.
Your computer is doing scary robot voice.
Okay, so what I'll do is I'm going to leave and come